In this video, I'll be teaching you guys about direct comparison tests. Now, it's important that you watch at least the entire introduction of this video, because if you do some of these things wrong with the direct comparison test, you'll make a very grave mistake that might cost you a couple points or even all your points on your questions on your exams. Because direct comparison test has some very annoying specific conditions that you will kind of have to memorize unless your teacher gives you a sheet. So I'm going to name all those conditions for you in this video so you don't have to worry about anything else. So I don't leave any space for error, I guess, as well. So first thing about the direct comparison test, well, whatever function we have inside of your series, whatever your sequence is called a of n. All right, this is called a of n, and it follows some format like so. You have some constant at the top. This could be 10. This could be 6, doesn't matter. This could be 16, some constant. It could be a million, for Christ's sake. All right, it just has to be a constant in the numerator most of the time, and I'll get into that later. But in the denominator, you're going to have some n value, which is the value of our series, to the power of something, k, right? So it could be n to the power of 3, it could be n to the power of 2, doesn't matter. But here's the thing about the dot dot dot. The reason why I put dot 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 here is because n to the power of k is the largest exponential value. So if you had n to the power of 3 plus 2n plus 1, n to the power of 3 would be n to the power of k in this case. And the reason why I'm specifying this is because let's actually use this function. The whole goal of the direct comparison test is to find some function called b of n. You want to find b of n. And the reason why it's called comparison test, direct comparison test, is because, well, we're using another function. We're comparing two sequences, b of n and a of n. So we have to find b of n. Well, how do you find b of n? Well, the thing about b of n is that we need to follow this. So assuming that both sequences are positive, a of n must be less than b of n. All right, it must be less at all corresponding terms. So at the first term, b of n must be greater. So first, b of n has to be greater than or equal to a, or for your second term, right, b of n has to be greater than the second term of a. So this is an important condition in the direct comparison test. Some teachers may want you to write down this condition in order for you to proceed on to your question. So keep this in mind. B must be greater at all values than a, right? B of n, the sequence b of n must be greater at all values than a. Well, how do you find b of n? Let's get into that now. Well, in order to find b of n, it's very simple. You keep the same, let's write b of n up here. You keep the same numerator, 10, right? And you just simply write down the largest exponent and its coefficient. So if there's a 3 here, right, you write down 3 n to the power of 3. So you have to write down the coefficient as well. Okay. But all you have to do is write down the largest exponent in the numerator and the largest exponent in the denominator. Now, the reason why I say largest exponent in the numerator is because technically 10 is to the power of n to the power. 10 is basically implicitly times n to the power of 0, which is equal to 1, right? N to the power of 0 is equal to 1. So n to the power of 0 is the largest exponential value of the numerator. If you had n up here, n to the power of 1, let's say, you would have to write down 10n. Okay, but we're just going to worry about 10 over 3 to the power of n, 3 times n to the power of 3. Now, in this case, b of n is actually greater at all points or at all terms because we have more values at the denominator. So plus 2n plus 1, right? That's just going to increase the denominator value, which decreases the value of the number. So at all points of b, at all terms of b, corresponding terms of b, are greater than the corresponding terms of a. Great, check mark, we reached this first condition. Okay, now that we have this, we need to write this down. And this one is the bane of my existence when I was learning this. But basically, it states that if b of n converges, so does a of n. A of n converges as well. But if a of n diverges, b of n diverges as well. Now, here's the annoying part about this condition. If b of n diverges, it tells you nothing about the, you get inconclusive as your result. It tells you nothing about a of n, your original series. So this right here is very annoying. If b of n diverges, then you got nothing. You got nothing. All right. this is important to keep in mind because we cannot say that the series diverges because b of n diverges. We need to use a different test, and you'd likely just use divergence test. Okay. So if b of n diverges, the test is inconclusive. Do not say that the series diverges based off of b of n. So these two specific conditions are kind of like the heart of direct comparison test. So you just memorize this, right? If b of n converges, then a of n converges. So let's go ahead and test this out. Well, we found b of n here. All right? B of n is just simply we kept all the largest exponents in the numerator and the denominator. So let's go ahead and test out if this converges. Well, simple enough. This is just a p-series problem, right? We have a simple number at the top and a coefficient that we can just kind of ignore. So basically, once you have b of n, that's when you use p-series. All right? You usually use p-series at the end of your direct comparison tests. Let's go ahead and use p-series for this. Well, we have an exponent, n to the power 3, so therefore p is 3. Remember, p-series just states that if p is greater than 1, then the series converges. If p is less than or equal to 1, then the series diverges. And clearly, 3 is greater than 1. Therefore, b of n converges, right? So we determine that the comparison sequence converges. Well, since b of n converges, a of n also converges. Therefore, we can say that a of n converges as well. Therefore, this series right here actually converges. Now, in the case if b of n diverges, again, I'm going to say this multiple times. In the case if b of n diverges, then that doesn't say anything about it, okay? If this guy diverges, let's say if b of n was, I don't know, for our imaginary, don't worry about this guy anymore. Let's say b of n was for our imaginary function, like 1 over n, okay? Then we cannot conclusively say that a of n also converges, all right? B of n here diverges because p in this function is just 1. And this is inconclusive, all right? You need to use a different test, likely limit comparison test. All right? But keep that in mind, okay? If b of n diverges, doesn't say anything about a of n. This is an important thing to remember. It can mess up a lot of students. And maybe your professor might put that as a trick question on your exam. So let's move on to some problems to actually show you how to do this. So for this problem, I mean, like, most of you can already look at it and just determine to use p-series and just completely ignore everything else. But a lot of Calc 2 classes are kind of rigorous, and they just want you to write down the steps for the direct comparison test. So that's why I'm making this video, of course. But first things first, we want to determine a of n. So a of n is the original sequence of your series. So we need to find what b of n actually is. So what is b of n in this case? Well, b of n is, remember, we only care about the largest exponents at the numerator and denominator, which is 8 over n to the power of 2. All right? Now, here's the thing. I mean, like, you can kind of write down 1 over n to the power of 2. Although this doesn't really necessarily meet the condition where a of n is less than b of n. A lot of textbooks just completely ignore the numerator in the what's it called? The constant in the numerator, and just write down 1 instead. So in this case, we'll just use that, actually. Oops. So 1 over n. All right, well, since b of n, we have b of n now, we need to determine whether b of n diverges or converges. So technically, we can use p-series here. So p in this case is equal to 2. And since p is greater than 1, the series converges. All right, b of n converges. Converges b of n. All right, and remember, direct comparison, b of n converges. That means a of n also converges. All right, and if a of n diverges, then b of n also diverges. So in this case, b of n does converge. So this meets one of the conditions of direct comparison test. Therefore, since b of n converges, a of n also converges. Therefore, this series right here also converges. All right, let's do this one. So right here, we need to recognize a of n. So now that we have a of n, we can write down some b of n function. B of n sequence, sorry. So what is v of n in this case? Of course, we only care about the largest exponents in the numerator and denominator, so we kind of just get rid of this plus 1. So we have 3 over k. Alright, let's turn this into 1 over k, since this makes it easier to look at. And we determine, using p-series test, that since p is equal to 1, we look at the conditions for p-series. If p is less than or equal to 1, then the series diverges. Alright, so since p is equal to 1 in this case for b of n, this guy actually diverges. So b of n right here diverges. So since b of n diverges, our test results are inconclusive. Yep, it's inconclusive. Okay, so because remember, b of n, if b of n converges, I shouldn't write this down every time. Jeez, man. A of n converges as well. If a of n diverges, then b of n also diverges. But none of these conditions state that if b of n diverges, a of n diverges as well. Right? So right here, we have inconclusive. None of these say b of n diverges at the beginning. Right? So boom, this is inconclusive. You would need to use a different test for this, likely limit comparison test.